Hello. Having discussed the process of radioactivity in the last class, we are now ready to talk about nuclear energy. Well, all of you now know that energy and mass are equivalent. There is an equivalent relation between energy and mass. And what is that relation? We have E equal to mc squared. And therefore, any discussion on nuclear energy must relate these two, mass and energy. Now, what is the unit for measuring mass? In the ordinary world, when we can all see and measure things easily, we use kilogram to measure mass. But when you want to measure the mass of subatomic particles, we will use a much smaller unit. It is called the atomic mass unit, AMU, or simply, very often, we will call it the unit. Now, what is an atomic mass unit? There is a big history behind it, but we don't have time to go into that history. But I can say the present understanding of an atomic mass unit is 1/12 of the mass of a normal carbon atom. Carbon-12 is the standard. So 1/12 of the mass of carbon-12 is considered to be 1 unit of mass at the subatomic level. In fact, this is the same as 1 gram divided by the Avogadro number. What's Avogadro's number? The number of molecules in 1 mole, or number of atoms in 1, well, that will be 6.03 times 10 to the power of 23. So 1 gram divided by 6.03 times 10 to the power of 23, you can do that approximately. That will work out to 1.66 times 10 to the negative 27 kilogram. If you work out this, that will give you in gram, 1 gram divided by this. And that will give you approximately 1 atomic mass unit is 1.66 times 10 to the negative 27 kilogram. Well, that will be the unit for measuring mass. What is the unit for measuring energy? We have already seen that. Energy is measured in a unit called electron volt. What is an electron volt? It is the energy acquired by an electron when accelerated by a potential difference of 1 volt. Now, what is its value? It will be 1.602 times 10 to the negative 19 joules. So 1 electron volt is 1.602 times 10 to the negative 19 joules. Well, we have now unit for measuring energy, unit for measuring mass, and there is a relation connecting the two. So we are ready to talk about nuclear energy. In the scale of atomic mass unit, the mass of a proton is 1.0073 unit. How about that of a neutron? Is the mass of a neutron the same as that of a proton? Well, the mass of a neutron is 1.0087 unit. Why? What's the difference? Why are these two masses different? Well, we have seen in radioactivity that a neutron can degenerate into a proton and an electron. So the mass of a neutron is actually greater than the mass of a proton. Well, the reason is much more complicated than the one I just said. The mass of an electron is 0.0005486 of an atomic mass unit. Well, If you add these two, therefore, if you add the mass of a proton and the mass of an electron, will you therefore get the mass of a neutron? Actually not. So the explanation of why the mass of a neutron is greater than that of a proton is rather a complicated one. We will not go into the details there. Now carbon-12 is the standard, as I told you, has a mass of 12 atomic mass units. By definition, an atomic mass unit is 1/12 of the mass of carbon-12. It has 6 protons and 6 neutrons. So let's calculate the total mass of these. The total mass of 6 protons, if you multiply 6 by the mass of a proton, you will get 12.096 units. How about the mass of how about the mass of 6 neutrons? Well, what I did is I calculated the mass of 6 protons and the mass of 6 neutrons, which came to 12.096. Well, is that a mystery? You know that carbon-12 consists of 6 protons and 6 neutrons, and the total mass of carbon-12 is 12 atomic mass units. But you take these particles separately and find their mass, the total mass is 12.096 atomic mass units. What does it mean? It means when you bring these particles together to form the nucleus of carbon, some mass seems to disappear. We lose a part of the mass of these particles. So when a nucleus is formed by combining several particles, some mass is lost. Now, how can some mass get lost? Well, how about the conservation of mass and conservation of energy? Now, the lost mass is actually called mass defect. So what is mass defect? When several nuclear particles are brought together to form a nucleus, the total mass of the particles the total mass of the nucleus seem to be less than the total mass of the individual particles. And that mass difference, or the apparent mass lost, is called the mass defect. And actually that mass is not lost, because there is an equivalency between mass and energy, E equal to mc squared. That becomes energy, and that energy is what holds the nucleus together. Well, that's an important concept. So the energy that holds the nuclear particles together is called the binding energy. And where does that energy come from? It comes from the equivalent energy of the mass lost, or the mass defect contributes to the binding energy. When nuclear particles escape the nucleus, well, if nuclear particles are taken out, then a part of this binding energy must also come out. And that is actually the origin of gamma radiation. We discussed in the last class that when an alpha particle is emitted by a nucleus, it is very often accompanied by a gamma radiation. Why? Because alpha particle means a part of the nucleus is torn apart. So the energy that binds those particles within that nucleus has to be released when the particle is broken open or broken away from the nucleus. And that is the origin of gamma radiation. If a massive nucleus splits into 2 pieces, now that's a different story altogether. If a massive nucleus can be made to split into 2 pieces, then the energy holding the pieces together, the binding energy, can be released. So one way to obtain a large amount of energy is to make a large nucleus split into 2 pieces. The total mass of the pieces is less than the mass of the original nucleus. And that difference in the mass defect, is converted to energy according to Einstein's mass-energy relationship, E equal to mc squared. So the binding energy of the nucleus of any isotope can be calculated from the mass defect of the nucleus. Well, we will not be doing all those things. I'm going to condense the whole chapter on nuclear energy into this 1-hour lecture. So you can imagine how much we can actually do. Now, the binding energy per nucleon is an important indicator of the stability of the nucleus. Higher is the binding energy per nucleon, more stable that particular nucleus is. Now here I have a picture of binding energy per nucleon, and binding energy is given in millions of electron volts. Now you must get used to electron volt. Iron, for example, is a very stable element. The nucleus of iron is very stable. Now, the binding energy per nucleon is about 8.8 million mega electron volts. Now, as you go to the left of iron and to the right of iron, binding energy per nucleon decreases. That means they are less stable. So, what happens if an element over here, a very heavy element, splits into two pieces? Sometimes they do that in order to achieve stability. When they do that, the product may be more stable because the products may be more in this region. So, the greatest binding energy per nucleon occurs near the mass number 56, which is that of iron, and decreases both for elements to the left and to the right of that nucleus. Now, more massive nucleus can gain stability. Nuclei in this region can gain stability by splitting into smaller nuclei, releasing their binding energy. Now, a converse effect can also happen. Small nuclei here can combine, releasing their energy, and that will be the process of nuclear fusion. And when splitting occurs, that is the process of nuclear fission. So both these, fusion and fission, is actually the process of releasing the binding energy. When small nuclei come or fuse together to form bigger nuclei, the binding energy, equivalent energy, is released. When very heavy nuclei on the right split into smaller pieces, again the binding energy is converted to energy. Well, if you look at these two lines, the slope of this line is much larger than the slope of this line. What that means is the energy released during fusion process is much greater than the energy released during fission process.